Welcome to Unit 4. So you're moving through the course pretty well at this point. This unit is nice and short, only 6 lessons. It's also nice in the fact that it doesn't require nearly as much rigor and practice as the previous unit. You will want to do practice questions, absolutely, and I'll be posting ones for you to use, but it's definitely a lot less rigorous than our previous unit. So good news, you should be able to move through it pretty quickly. So we'll get started with lesson 1. Which is the fundamental counting principle. So we consider these examples and then we'll get into what it actually is. Example 1, a fan has 3 settings, off, low, and high. How many ways are there to set 3 fans? So we could talk about different settings like fan 1 could be set at off, low, or high. But then fan 2 can also be set at off, low, or high. And fan 3 also has those 3 options, off, low, and high. So because each fan has 3 options, and I don't have to have all of them on the same setting, that's not anything that I'm told. I could literally choose any one of the 3 for all 3 of them. So in general, I have 3 options here, 3 options here, and 3 options here. And that means that overall, I would multiply them together, and I would get 3 to the power of 3, or 27 options. If you don't believe me, then we could go 1 option is all off, 1 option's all low, 1 option's all high. So those are the straightforward ones. We could go off, low, high, off, low, high. We could go off, high, low, low, off, high. Yeah, and so if you walked through all of the different options, you would end up getting 27. I don't even have 27 colors to choose from, so I can't even highlight all the paths we could choose. But that's how we do it, is we would multiply them together. Example 2, at a grocery store there are 2 lineups. Lineup 1 has 2 people. Line 2 has 3 people. If they were to rearrange themselves but stay in the same line, how many different possible lineups are there? Well, there's 2 possibilities, 1 person in front or 1 person behind. There's 3 possibilities here. We could have the front person stay in the front, be in the middle, or in the back. Actually, person A, B, C. Then we could also have them A, C, B, and then we could put person A in the middle and go B, C, or C, B. Or we could have person A at the back and go B, C, or C, B. So all of a sudden, this line has 6 options, where this one only had 2, A, B, and B. So we've got 2 options for the first line, 6 options for the second line, and so what we get all together is 2 times 6, which is 12. And the reason we multiply again is because for each, so if I just chose AB, I still have 6 options. But then if I chose BA, I'd have 6 options for the second line. So I've got 2 different settings where I'd have 6 options for the second line. So that's what gives me that 12 versus 27. Okay, so the more kind of situations, more layers I add to a problem, the more complicated it gets. I wanted to just multiply by 3, but that wouldn't have given me all of these options. That would have only given me these 3. And I would have missed the ones where we could have switched B and C without moving A. So, what is the fundamental counting principle? Well, that's the fundamental counting principle. We'll put some math jargon to it. So the fundamental counting principle is if there are some number of different objects in one set and some number of different objects in a second set, okay, and the key thing is that they are different objects, then the number of ways of choosing one object from each set is done by multiplying them. Okay, in other words, if one event can occur in A ways and a second event can occur in B ways, then the number of ways that both events can occur is AB ways. If that's not making sense, you're like, that's not clear. Let's do some more examples to try and figure that out. So example 3, for an online banking account, the minimum security standards require a password to have 2 letters followed by 5 digits. So I've got 2 spots, and these both have to be letters. And then I've got 5 digits, and they have to be digits or numbers. All the letters and digits may be used more than once. Okay, so we look and we say, okay, well, how many options do we have for letters? In general, our alphabet is 26 letters long. So in both of these spots, we have 26 options. For digits, we've got 10 options. Okay, so letters A, B, C, etc. 0, 1, 2, etc. all the way up to 9. Okay, so we've got 10 digits to choose from. So 10, 10, 10 options, 10 options, 10 options. And the reason that that number doesn't change, I always have 10 options, is because I can use the same number again and again. So I could choose A, 8, 8, 8, 8, 8, and that would be my password. That is one option. I could also choose BD19865, and that would be another option. In one option, we've got repeating. In another, we don't, but either one is just as acceptable as the other because there's no restrictions on my password. Other than that, first 2 pieces have to be letters, and the last 5 have to be numbers. So once I've established how many options I have for each place in my password, I just multiply them. So I'd go 26 times 26 times 100,000, and that will get me my answer. So 6. Okay, so we've got 67,600,000 options. Which means that hypothetically, everyone in almost the whole world could have a different password. So that's how the fundamental counting principle works. So the key thing to note is that setting up kind of like places for different choices kind of is a helpful way of laying it out. So when we see that again in example 4, where we have how many different license plates are possible if 3 letters must be followed by 3 numbers. So again, 3 letters must be followed by 3 numbers. So the typical friendly Manitoba license plate. So each letter, again, we can have repeating letters in our license plates. That's entirely possible. So I've got 26 options for each of these places. And I've got 10 options for each of my digits because I'm allowed to have the same digit. So again, I would just punch this into my calculator to get this answer. So we get 17,576,000 options, or different license plates. Okay. So varying, even though like this had more options in terms of like places, and we changed the numbers that we were working with, so it's going to vary our solution. But again, each of these lines represents a place where I am making a decision. There's a different choice that needs to be made. Example 4, how many 4-digit, so I'm talking 4 digits, so I'm going to put 4 places to work with, even numbers. Now this is a key thing. Can be made using this specific set. Okay? So even numbers have to be divisible by 2. So when I see even numbers, I know that my last digit must be 2, 4, 6, 8, or 0, but 0 is not part of my possibilities, so I'm not going to include that. So when I look at this place value, the last digit of my number, I know that it can only be one of these 4 options. So before I start filling in the beginning stuff, I am going to put a 4 here, because it could be 2, 4, 6, or 8. Those are my only options. Now, again, it doesn't say that I'm not allowed to repeat, which means that the rest of this digit can be formed using any of these numbers. So I need to count 1, 2, 3, 4, 5, 6, 7 options. So for each of these, I have 7 digits to choose from. But then that last one can only be 4 because I have to use an even number. It's going to be 5,488 options. Even digits. Oops. So with that in mind, do a couple more examples. I hope you're feeling kind of comfortable with that. If you want to pause and try these examples on your own, that's not a bad idea either, but I will walk you through them. So if you want to pause, pause now. Okay, so example 6 looks at how many 5-letter words. So again, 5 letters are being filled in here. Can be formed using the letters in the word factor. And when I look at the word factor, I notice one thing about all of them is that they're all different letters. Which means that I've got 6 to choose from. Words can have repeating letters. Book, look, it doesn't matter. So I could hypothetically reuse these letters, and so I've got 6, 6, 6, 6, and 6 as my options because I could use any of the letters anytime I want. So that gives me 7,776 options. Okay, and so the key thing to note here is that we use the word words very loosely. And it's really just referring to arrangements of letters. So your English teacher would not call all 7,776 possibilities words, because I'm pretty sure that this is not a real word, but it would count for our purposes. English class, not so much, but for math, absolutely. Okay, example 7. How many 6-letter words? I'm going to put 6 lines for my 6 spaces of my letters, beginning with F and ending in a vowel. Okay, so whereas example 6 was wide open, we had all the options in the world. Now we are getting some restrictions, which means we should have fewer options in the end. My answer should be smaller for example 7 than example 6. And I need to kind of look at those restrictions before I look at anything else. So beginning with F means that I'm still using the word factor. There is only one F to choose from, so I literally have one option as to what's going in that first blank. It can only be F. My next restriction is that it ends in a vowel. Well, I look here in my options for letters, I've got 2 options. It can either be A or O. Still doesn't say that I'm not allowed to repeat these letters, though. So for all my remaining blanks, I could still use F again. I could still use whichever vowel ends up being in the end. So I could still have 6 options for each of these. And I would multiply them all together. So 2,592 words. Okay, and so again, examples of these would be F, like in factor, wouldn't work, but TRO would work. But also, so could, okay, both of those would be acceptable, even though, again, they're not technically words based on your English definition, but they are words in math. Example 8. How many 5-digit, so again, starting with my blanks, my spaces to fill in, even numbers, so again, that means I'm looking at 2, 4, 6, 8, and 0 at the ending. And again, I'm allowed all of those. So that leaves me with 5 options at the end. Then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 options for every other place, because again, I am not told that I'm not allowed to repeat. So this gives me 50,000 digits. Okay, so that's kind of how the fundamental counting principle works, is you always kind of like create your spaces for every decision you're going to have to make, and then from there you fill in that line with how many options do you have for each of those decisions. So for the first place of my 5-digit number, I have 10 numbers to choose from. In my second place, I have 10 numbers to choose from again. In my third place, I have 10 numbers to choose from because I'm allowed to repeat it. And in my fourth place, I have 10 numbers to choose from because I'm allowed to repeat numbers. But my last place is only allowed 5 options because I'm given that restriction of even numbers. So I like to kind of, in general, approach these problems as 1, use blanks to represent each choice or scenario or decision, whatever word you want to use. Okay. 2, I consider restrictions. And then I fill in my blanks with the number of options to choose from. So it's kind of my general approach of how do I do these types of questions. And then you multiply them all together. And that kind of goes without saying, that's part of the rule, but 4 multiply. Okay, so that's the basics of our fundamental counting principle. We added some restrictions into some of these examples. We will get into situations where we start having like, what if 2 of my options are the same? Like if instead of factor, we had used a word that had 2 of the same letter. We will be looking at that, but for this lesson, we didn't have to stress about that, so we just considered what options were available to us, how many of those were there. Okay, so those are the general steps. So I will post some work for you, and then you can move on to lesson 2.